Okay, so in the for the recording, I started a little bit late, just going over the table of contents right now. For the very last thing for today's menu, we're going to go over publication. This includes going over renders and materials of the parts in your assemblies, setting up cameras, setting up lighting, setting up renders and backgrounds and stuff. So all those things are super nice. There's also a neat feature in SolidWorks, like giving you an exploded view. Basically, if you have a robot with multiple parts, it just explodes them outwards and looks really nice. So if you want like publicize stuff for your team or robot, some good tools to have. Okay, with that said, let's go ahead and get started with this. Okay, so let me close this guy out. And I'll go ahead and get started with the first one on the menu. So first one up is basically mates in assemblies. When you have an assembly, it's made out of multiple parts or even sub-assemblies. So assembly consists of a bunch of things in it. You want to make sure that those guys are all attached to each other. So you will generally be using the mate tool. So it's located here in the assembly tab, big paperclip. It lets you mate things together. You'll see here, everything's already mated. So might not be a very good example here actually. But we'll see here, there is a double paperclip called mates here. It shows you everything, how they're connected together. So for example, we've been using a lot of the basic mates just to fix things together. So these two, the axes of the rod and the rod itself are going to be concentric. So they're locked in place in that one direction. And then we will then set the width to be equal. So it's centered within the two. So there's a bunch of tools like this you can use. Let me just show you what's going on inside the mate feature. So when you click on mate, it shows you this large window on the left-hand side. Basically, you select two or more things to mate together, and then you select what type of mate you want to do. By default, these ones are the basic mates. They do the job to get things done. They make sure that things are anchored to each other. You're probably using coincidence and concentric a lot. So those things, hence the name, they just make sure that things are touching, coincident, or that things are concentric, circle within a circle, or cylinder within cylinder kind of thing. You'll usually need like, I don't know, 3 concentrics to make sure something's locked down, or a concentric, sorry, 3 coincidents to make sure something's locked down, or like a concentric plus a coincident, something along those lines, to make sure something's locked down. And you know something's locked down when you try to click and drag it. That's not a good one, actually. That one's movable. Try to click and drag it. It's just like fixed or something. I think this one should be. Oh, it's not locked down. Okay. So that one is rotating. So we didn't fix the rotation of that. That's actually not a big deal though, but it's just a screw. But once you do fix something, it'll be like fixed in place because it's anchored at 3 in all dimensions. One of the other things I want to show you was the more advanced mates. So you saw here in the mates tab, we have a bunch of stuff. Width was not in the basic mates tab, I believe. I think it's under advanced. Yeah, so you see here 4 tabs: standard, mechanical, advanced, and analysis. Most of the time, standard mates, once again, they do the job, mate things together, keep them together. Also some fun ones though, especially in mechanical or advanced. In mechanical, you have a lot of things that let you have stuff that moves around. So in this tab, you might be using like stuff like hinges or maybe gears, possibly even screws a lot. You don't need to use the screws one for screws like this. If you want to be super cool and like have the threads align and stuff in the screw and in the recessed hole for the screw, then you can use the screw mate. But for the most part, you just get away with just doing concentric, and then make sure that the head of the screw is coincident with the flat top. Of course, that does mean that it can rotate it, as you saw before. But if you want to get rid of the rotation, I think you should use screw. It'll let you rotate it, but it'll then follow the threading of the recessed hole. So some cool stuff there. I never use it because it's a big headache. I just do the concentric and coincident. So in addition, advanced tab has a lot of cool stuff as well. So width, as you saw here, lets us space something between 2 things without having to specify like this is like the center plane or something. Basically, you select 2 faces and 2 tabs and make sure that the space here is same as the space here. Also, some other fun ones. These 2 are probably the most important ones, I think. This one is it's fixed minimum and fixed maximum distance, and it can vary between those minimums and maximums. So you see how that is used here in the claw. I believe it is used, where is it? A limit distance over here. So this is a piston mounted to a claw. So for this design, we wanted to have it a single piston, like a claw machine pretty much, opening and closing the jaws. So to do that, we have set a minimum and maximum distance for the piston length. So we have minimum of 5, maximum of 45 millimeters. And if you go out of the mate and try to drag stuff, you'll see that it does move around. We can close and retract. So it's a cool way to add some, what? It's fixed? No way. Okay, there we go. That was not fixed. So it lets you make cool dynamic assemblies that actually move. You can like show them off. It looks really nice when people come and ask you how it works if you don't have the robot with you. So it moves, it shows you the range of motion and lets you see if it's going to work before you even print it out or build it yourself. So good to have under your belt. These mates let you restrict movement in certain dimensions, lets you retain some movement in certain dimensions. And yeah, there's a lot more mates than that, but for the most part, the basic mates, coincident, concentric, and some of the more advanced ones like limiting distance for pistons and possibly rotation stuff could be useful for you as well. Okay, assembly management. So you see here on the left-hand side, it is pretty messy. It's a bunch of stuff. Some of them have like numbers in front of them, like part numbers from like McMaster. When you have an assembly, especially when it has a lot of parts, you will want to use folders. And especially you want to make sure stuff is named appropriately so you can find where it is. So just earlier, I made a folder for attachments that contains like a bunch of screws and stuff. See how those orange bounding boxes hover over the screws and nuts. You can add stuff to folders here. It doesn't really change anything. It just makes sure it's nice and grouped. You can find where stuff is. You just hide it when you don't want to see it. You want to focus on the big pieces. So to do that, you click on one or more. You can click on one and control click on other ones, or click on one and shift click on another one. Select everything in between. So select a multiple or just one, right click, and hit add to new folder. Alternatively, you can just drag and drop it into a existing folder. So yeah, just be sure to use folders when you're making large assemblies to make sure things is organized. You can still keep like the main body pieces like in the top root level. That's fine. But for large, small attachments, you probably want to stick to keeping those tucked away in a nice folder somewhere so they don't get everywhere and junk up the left-hand side. In addition, yesterday we talked about configurations a bit actually. So configurations, that was in parts. In a singular part, you can make configurations and stuff. You can do the same thing for assemblies as well. Making different configurations of assemblies. You can like have like one where your robot has like the jaws open or something, and then one with this closed or something. You can do that too. It's very similar. Go to Configuration Manager, add a configuration, right click on it, add configuration, or alternatively, add a sub configuration, derived configuration. So you can do that, and it'll show you a bunch of stuff. It's very, very similar to the part configurations, as in you give it a name. Make sure you select suppress stuff. Depending on how you want to have it set up, you can check one, check both, or check none. But you'll probably want to suppress some things for your configurations. Yeah, once again, if you have some questions, feel free to just speak out. Let me check chat. Nothing in chat so far. But if you do have something in chat, I'd appreciate if somebody can just speak up and voice the question someone else has, because I tend to forget and I don't see the notification. Okay, I think might pass the next one off to Naomi if you want to pull that up. Let me stop my share.
Okay, one more thing I want to note about organization is that you should keep all the files for an assembly and the assembly in the same file on your computer. Otherwise, you run the risk of SolidWorks not being able to find it, which is really annoying when that happens. Okay, so for mass properties. So I have here a really simple assembly, and I have applied materials to it. So when you do mass properties, it's really important that you apply materials to all the parts in the assemblies. Otherwise, this won't work because SolidWorks won't be able to figure out the densities of the materials. So I'm going to show you real quick how to do that. So first, I'm going to insert one more component. Let's do this circle. Okay. So I have my circle in my assembly. I'm going to real quick mate it somewhere. Let's mate it here. That was a horrible mate. Hold on. That was a really bad one. Okay, let's try that again.
Yeah, so that button name we just clicked, that lets you flip the alignment of the mate. So important thing to do if you ever get stuck and have something clipping inside of the object. Might need to flip the coincident mate.
Okay, that is good enough. So now my assembly is all mated together, and now I need to apply materials. So I'm going to right click on this, and this menu comes up, and at the bottom right here, it says material, and I'm going to come in and edit the material of this part. And I have all of these options here. And for the purposes of demonstration, it doesn't really matter. So I'm just going to choose hot rolled bar steel and apply it. And I think it's applied. So now I'm close. And you see the color is kind of changed. So I'm also going to show you how to change the material for something that already has a material, and it's pretty much just the same thing. So you right click material, edit material. You also have this little menu of like a shortcut. So I'm going to change this to brass. The color has changed. So now we go to the Evaluate tab and Mass Properties and Rebuild. And it comes up with this menu right here, and it gives a big summary of all the mass properties. So the important parts is the mass is 5.88 pounds, the volume, and the center of mass. That's everything else is kind of complicated, and you probably won't be using it, but those are really useful. Those are useful things. We especially use volume because we work underwater. So volume is useful for calculating the buoyancy of our ROV. So yeah, that's how you use the mass properties.
Next one up is, let me share my screen again. When you, as you saw in the image, just showed you mass analysis, you can see how massive it is, how much volume it takes, center of mass and stuff. And a short departure, you can also take a thickness analysis, see how thin or how thick stuff is. This can't be used on assemblies, only parts. So let me just demonstrate what I mean by that. Let me go ahead and open up a part. So I have here a little piece. I want to go ahead and see how thin stuff is. Because I want to know if like this is too thin, this distance from the hole to the left side is too thin to be printed or something, and might just snap off immediately. I want to know how thin that is. I want to know how thin this diagonal is. You could, of course, just manually measure it using the measure tool, but then you have to measure everything, and you don't want to do that. So just press the thickness analysis. It's under the Evaluate tab. So analysis parameters, thickness scale, nice color scale. I think I hit okay. Oops, I need to hit sort of face, I believe. Show thin regions. It's not showing up. I think I select this even lower. Okay. Okay, so it's also showing me stuff inside. So in this device, there are small screw holes that we're gonna thread some rods into to secure this stuff So you see here, the scale, red means really thin, green and blue means okay-ish. So you see here, it gets really thin around here when I cannot even see that. Let me see if I can orientate the screen even better. But okay, yeah, so this hexagonal face is very thin to the roof. So that might be something to look out for. It's about 1 millimeter. If we try to print this, it'll probably be okay, but be careful, it might snap off. So keep that in mind as you design your stuff. You use your thickness analysis to see if something is really thin, something you haven't considered. I did not consider this actually. I was only thinking the diagonals here might be too thin, but this stuff's really thin as well. Of course, I think it's because I selected my local analysis face to be only the top. So it only checks from a face down view. Will the thickness from the face down be very thin? So it did not measure this, only measure this. I think if I cleared here, and I will do it for everything, I think. Let me just do a quick check. Okay, it does it for more things now. So not everything that I wanted, but good enough. Yeah, so use thickness check to see if stuff is too thin or too thick to be printed. Okay, then keep opening the wrong PDF. Okay, yeah, once again, only for parts, unfortunately, but you can just run it for multiple parts in the assembly, so that also works, but just a bit of a hassle. And next one I want to show you is or do you want to show this one, Naomi, actually? I need to get stuff prepped for the next part.
I don't think I have the right part open for this, but I can make something interfere. Okay.
Gotcha. Okay, thank you.
All right. So I'm gonna real quick go back to that horrible mate I did earlier. So perfect. Now the interference detection shows you where parts are overlapping in your assembly. So we can either select the whole thing, or if you don't want to run that, say you have a really complex assembly, you can clear that and you can select only the parts that you want to check for. So if I calculate this, it'll get mad at me and make an annoying sound and say this part is no good. And if there were more, it would show each individual interference in this box here. So I can also show if I did the whole thing. It shows the same thing because there's only one interference.
Yeah, one thing to note when you do the interference check is if the number to the right of the interference is really, really small, it's probably a very, very small clip. Like, I don't know, if you're with the threads of your screw and like digging into the wall of the hole, then that's no big deal. But if it's something larger, then something's an issue. You need to check your mates, see if stuff is clipping too much. But for very small numbers that happen, it should be okay. Okay, and then next I want to show you guys some of the CAM stuff that we do as robotics. So CAM, computer aided manufacturing. It is basically just generating a toolpath for a large axis mill to cut stuff out of a big piece of stock material. Reverse 3D printing, pretty much. Instead of printing something up, adding material, you just remove the material to get what you want. So let me see if I can open up the part that's being talked about here. So we use the plugin HSMWorks from Autodesk. It's a Autodesk-made plugin for SolidWorks, made by Dassault Systems. So it's kind of weird. There is also in SolidWorks like the built-in CAM solutions and CAM plugins, I believe, but we've been using HSMWorks, previously known by HSM Express, and it has been doing the job pretty well. So you see here a gigantic piece of black plastic, HDPE. It's about water density plastic. Really nice for underwater applications because it doesn't really add to the buoyancy all that much. And what it does add is immediately canceled out. So you notice here, there's a bunch of dimensions on the right, smart dimensions, and it's like this whole thing is like encased in a yellow bounding box. So I'm currently in the CAM manager here on the left. You'll notice I have enabled the, I believe it was here under add-ins. I currently have the HSMWorks plugin added here, I believe. HSMWorks, so it's currently on. You can also use the built-in cam stuff here, but this stuff works over here as well. So basically, when you want to use a CNC mill or for generating cam job, you will want to use SolidWorks and then generate a toolpath here. So I have here, there's currently job, whatever that job is. I think it's just the default job, nothing in it. And job 1, which has some stuff in it actually. So look here, when you generate a cam job, you need to take note of certain special considerations, specifically what size drill you're going to be using, as well as what sort of path you want to cut, what holes you want to cut. As you see here, you can select the drill. We're currently setting a 3.175 millimeter drill. So that one's really nice because we want to cut out a bunch of M3 holes for modular attachment mounting on the panel. So that means you just dig down and dig straight back up without needing to like dig down, wiggle around, and dig back up. And of course, if you select the drill too large, you can't dig through the holes because it'll just make the hole too big. So consider the drill size as you make the jobs and as you design your parts as well. And you see here, dx equals 0, dy equals 0, dz equals 0, WCS. I think that's world coordinate system, I believe. I forgot what the W stands for. So I think it's world. But basically saying the drill is going to start at 0, 0, 0. You're going to zero it at this position. You're going to, when you put your stock material in and you start the cam machine, CNC mill, when you zero it, it's going to say, oh, I'm at 0. And that 0 is defined as this coordinate value. So that is something to consider. And then we have here, we have contour, bore 2, and 2D contour number 3. So contour 4 here digs out multiple things. These large notches for interlocking with other large HDPE plates for the body of the robot. So basically what we've done here is we've set the settings for the drill. And then we have a bunch of different tool paths that will be done in sequence. First, the drill will go through and dig out these large notches for interlocking with other plates. And then it will lift up and go to the next guy, the next job, which bore 2 is going to dig out large mounting holes here, here, and for these guys over here as well. And for the top handle for padding. And then lastly, it's going to do the outside edges. So the blue lines here notify the outside edges. I'll go ahead and show you. You can also, if you right click on it, you can see a bunch of different stuff. The most important ones here are probably generate toolpath, simulate, and post-process. These 3 are probably the most important. Generate, simulate, post-process. So I'm going to go ahead and click on simulate, show you guys what will actually happen. I wish I was at lab. If I was at the lab, we could probably actually show you how it works, but it takes a while to set up. But you see here, that little guy here, that is the M3 drill, 3.175 millimeter diameter drill. And if I click on the play button, it's going to start moving around. So starting here, doing the small holes first, and it's going around nice and easy. Oops, let me go right here, bump up the speed a bit. And then, yeah, it's pretty nice. It's like looking at the 3D printing slicer and just checking out how the thing's going to be cutting stuff. It's very similar to that. Layer by layer, path by path, it's going to cut out the material you want. And then, of course, once you have set up your paths, once you have checked a preview for any issues, you can then generate the tool path. Click on this button, it'll save some things. Generate the path. Sorry, I got the order wrong. Generate the path, and then you simulate the path, and then you can post-process it. So generate, simulate, and then you post-process. When you post-process, important things to consider is you need to select the right machine you're going to be using, because different machines have different capabilities, and they process decode the code that the file you're going to save to slightly differently. So we at SolidWorks, we tend to use the Inventables X-Carve. It's a 2.5 axis mill. 2.5 axes, basically, you can go in the X, Y direction, but Z only up and down, straight up. You can't like tilt it or anything. No fancy stuff, unfortunately. But it's rather cheap, like only like a couple thousand, I think. if you consider that cheap, that is. Okay. So you see here, yeah, just be sure to check the right box for your machine. You may need to go to your manufacturer and go to the support websites and download the right configuration files, but it should be in there somewhere. Okay. So what you just saw was me using HSMWorks and generating CAM toolpath and simulating it.
Can you actually go and open and edit up the job or edit the job? I want to like point out a few things. I accidentally deleted HSMWorks off my computer, so I can't show it. But so there are a few different options you have when you're selecting what type of thing to add to the job. You usually want to stick to drilling or 2D milling. Since we do routing, that's what we stick to. So drilling, you are going to be boring out holes. And can you go like the drop down tab for 2D milling?
Yeah. It's really slow here. Okay, so for 2D milling, I was just making a new drill. Okay, 2D contour. That's kind of weird, but this one also does the inside edges, so we can do this one. So let's take a look inside here. So this is one of the plates from, I think it was 2 years ago. So a bit outdated, but it still shows you everything that happens. Okay.
So a 2D contour is going to cut out a kind of weird looking shape like we have here, these little hourglass things. And I don't really remember all these little settings, but you want to select, I believe, the bottom edge of your little shape that you want to cut out. And then you're gonna have to adjust the feeds and speeds and stuff. And that's gonna depend on the material that you're using. Since we use plastic every time, it's the same for us every time, but you guys might use aluminum or steel. So you're gonna have to look that one up. And then we also use some other types of 2D milling. Can you do the little drop down?
Drop down, what, where? Oh, fancy. Okay.
Yeah.
Oops, I need to close out this one. And then let me, can you erase your annotation real quick? Okay, so here, what do you want to look at? Bore? That's just like straight down kind of thing, almost.
So yeah, bore is for boring out holes, and that's just gonna bore out with the diameter of your end mill. And that's.
Well, do notice, I want to cut it real quick. It will drill down, and if it's larger than the drill size, it will do a little wiggle around to make sure it's large enough. So not just the size of the drill, but also a little bit larger if you wanted to do that. So it's pretty versatile.
It cuts out circles.
Yeah.
Yeah. And then for other things, we use 2D adaptive clearing, and all of these basically, they're different for different types of cutting out. So they cut out different shapes, and so it's different for different types of shapes. Sorry, that wasn't very eloquent. But the really important thing that you want to do when you're setting this up is you want to make sure that the direction that your end mill is spinning with respect to the way it's moving is the correct direction. And that you can typically see when you do your simulation, but you set it up when you're setting up your job. And SolidWorks usually does a pretty good job of simulating that, but sometimes it won't show.
Yeah, I think I don't remember how I can check it. I clicked on simulate, I clicked on the play button, and then did it go? Okay, there it is. Does it show rotations?
It doesn't show rotations, but it'll show which side it's cutting out. And if it's on the wrong,
oh, I see. Spinning it says clockwise, 5,000 RPM clockwise. So clockwise, yeah, that's okay here.
Yeah, and if it's spinning the wrong way, then sometimes it won't generate the toolpath.
Yeah, so notice we are moving counterclockwise. We want it to spit out and spin clockwise. That way spit out the material behind it as it goes forward.
Yeah.
So something to consider as you generate your tool paths. So let me see. Okay, I think that was pretty good. I also wanted to go over, it's a big wall of text, but let me just go over this real quick. So with robotics, we have like a general workflow for how we tend to do CAM stuff. It's a long list, but basically we start in SolidWorks. We then design the toolpath using HSMWorks, and then we tweak it, check it, make sure it's okay. And then we go and save it and load it up on the laptop, go to the X-carve, our 2.5 axis mill, and cut it out there. So important key points to consider that I haven't already gone over is, let me see. All right, step 8, performing the mill preparation steps. So when you actually use a mill, you need to make sure it's like zeroed in and that the machine knows where the drill bit is, pretty much. To do that, there are some special tools you can use. Basically, since the drill bit is usually metal, you can have like another metal block right beneath it. When it touches it, it'll send an electrical signal and say, stop here, you're at 0, 0, 0. And then that's pretty neat. You remove the metal block and you're ready to go. Of course, you need to place your stock material underneath. So you just need to make sure you get the mill that you're using and the software that you're using to control the mill. Make sure that they both know how thick the stock material is, where the drill bit is at the very beginning, and then make sure your stock material is not going to exceed the bounds, or your drill is not going to like dig into the table. Generally, with most mills, I think they put some sheet of like protective material, like some scrap wood underneath, and then you put your stock material. So scrap wood, stock material on top, and then you have a drill. So even if you do dig down, it won't damage your table. Just dig into the scrap wood of the thing. That's how we have it here at Robotics, at least. Make sure there's some scrap wood underneath the stock material, so that we don't dig up the table. Just curious, are any of you guys familiar with using CAM stuff, CNC mills, etc.? Quick raise of hands, or if you want, you can just shout it out. Because I'm only very familiar with the Inventables X-carve. But if you guys have some experience, I'm also curious to hear how you guys have been using stuff. If not, no big deal. I don't think I ever had a mill at my high school. I don't think there was. There might have been for the machining shop. I don't think I've ever been there. But at least now, so at UCSC, we have a couple, so that's pretty nice. And then let me see. So some tips to consider as you do the CAM stuff. Consider like how important is the piece? Is everything going to be hinging upon it? If it is, you're probably in the right place. You want to use some CAM stuff and make sure you choose the right stock material that's going to be strong enough to bear it all up. But if it isn't, it's going to be a small minor piece. Well, why bother with CAM? It's a big hassle. Just 3D print it, especially if it's not going to be load bearing or anything. 3D printing will probably be cheaper, faster, and easier to prototype. And in any case, if you do CAM stuff, you probably want to do some sort of 3D prototype, or at least do extensive verification to make sure that your things are going to be okay. Because once you cut it out, it's pretty much not possible to add stuff back onto it. So be careful what you cut. And then if you're milling many small objects, how can you orient and fit multiple parts to be milled on the same piece of stock material, reduce wastage? So when you buy stock material, it's like usually a large sheet of metal or plastic, whatever. For us, we tend to like buy like, I don't know, 2 foot by 4 feet sheets of like, I don't know, I think it's 1/4 inch HDPE plastic. And then since some parts we need to mill out are pretty small, we can fit them alongside other large pieces to reduce wastage. So just be sure, keep in mind, how can I orient stuff to mill it out? Well, the chat box says, oh, we have a CNC for our FRCG. We don't use it for FTC. Cool, cool. Center design to third party. Yeah, that's also a good idea. Okay. So let me see. Oh, you saw on here, this is just a single part. You could also have an assembly with multiple parts on the same thing, and then just like set up like a bounding box of 2 foot by 4 feet, and then make sure everything's within that bounding box, and then generate tool path for everything at once. So that's also something you can do. It's not just single part. You can do assembly and then CAM that assembly. So that's what I tend to do to reduce wastage instead of just doing a single part like this. Because once you do cut out this shape on the board, then you have like 3 chunks left over. You have this large center chunk, small center chunk, and then the outside edge. And it's hard to use those pieces normally. So if you make sure everything is oriented in a line and fit it together on a single assembly, and then you can mill it all at once and reduce wastage. Okay. And then since we will probably be working with 2.5 axis mills like X, Y, and limited Z, no rotations, in the no pivoting, that is on the Z, pretty much. Consider how this will affect the types of objects you can mill, at least mill in-house. You can't really do like overhangs or something fancy like that. You can't really do like horizontal holes or anything because you got to cut up the roof to make sure you get the hole. So consider your limitations based on the mill you use. You saw here that we talked mostly about 2D milling. There's also 3D milling and some weird funny stuff. I think some of these should be doable by 2.5 axis mills. But for 3D milling, you probably want to see if you can limit stuff to 2D mill. Just the bores and 2D contours, probably the most, the bread and butter, I suppose, of your mills. And then what type of material are you milling? If you're going to be doing like plastics, you can get away with your standard drill bits pretty much, or maybe something a little bit harder. If you're doing metals, aluminum should be okay, I think. Check the drill bit, check also the CNC mill, see if they both can handle doing metals, especially stuff harder than aluminum. And of course, if you have something you want to mill out and your stuff in-house isn't strong enough or isn't good enough or isn't large enough, you want to outsource it to another company. It'll be shipping time, lead times, of course, more costs, but it'll be safer. Don't need to operate huge machinery, and probably also cheaper because you don't need to buy like the multi 10 grand machines to mill those out. How many axes can you get? I think there's like 2.5, I think up to 5 axes. HSMWorks claims to work with up to 5 axes mills. I don't even know how you get 5 axes, but I don't know. Sounds pretty cool. Okay. Did I skip something? Simulation. I thought I was supposed to go over something else first. Was I? So I talked about CAM, valuation. Okay, then simulation. Okay, simulation is going to take a while actually. Do you guys want to go over simulation now or take the break and then go for simulation? Because simulation will take, this will take a good 30 minutes-ish. I want to hear your votes on this one. I was originally planning to take a break at like around 3 o'clock. But since we got through things a little bit faster, we can take a look at simulation now or a little bit later if you like.
I think we should do questions, then break, then simulations.
Okay, sounds good. Questions, and then if no questions, we can go on routing cables and then simulations. And then break, questions, cables, break, and then simulations. Okay, that sounds good then. So any questions so far? So far we talked about assemblies, making stuff together, make sure stuff's nice and organized. We haven't talked about routing yet. We talked about evaluation tools, such as the mass and thickness checking, interface checking as well. We talked about CAM, how you can generate tool paths for your CNC mills and mill stuff in-house, using HSMWorks, some general tools, and a brief discussion on CNC stuff and metals, plastics, others. So any questions that arise so far, feel free to just shout them out or use the chat feature. See in the chat box, is CAM used to cut materials out to desired shape? Yes, CAM is computer-aided manufacturing. As I mentioned before, you can basically consider it as like reverse 3D printing. Instead of printing additively, layer by layer, you now cut layer by layer out of a large piece of stock material. So when I had this guy here, basically you can consider as if I had a large piece of black plastic, a rectangular prism, and then I use the tool path to cut out shapes. So I have this guy left over. Okay, and then as for another question, do you have to open a separate file in order to assemble stuff? Kinda, yes, you do. So in SolidWorks, you have SLD PRT files, solid part files, and solid assembly files, SLD ASM files. Assemblies are combinations of parts and assemblies. Parts is just a singular part, nothing else in it, just sketches and features. So when you want to make an assembly, file, new, and then nice handy 3 buttons, part, assembly, drawing. Usually you just do parts and assemblies, but you see here next description, 3D arrangement of parts and or other assemblies. So assemblies can have other assemblies in it. It gets a bit complex. It's assemblies all the way down kind of thing, but yeah, assemblies are nice. Good questions. I see a question in the chat as well. Okay, how do we set up something when cutting something out for a cam? Okay, so for setting stuff up here, or I kind of skimmed through setting up a contour pretty much. So let me go ahead and see if I can I'll remove the outside edge and redo this one. Okay, so if I want to add a new cut path to do, I will right click on the job I want to add it to. So I can add it to a different job if I want. I want to add it to this job. So it'll be all done in one go. So I'll right click on it, new operation. I want a 2D mill. I want to follow a contour, 2D contour. Oops, I got interrupted by the autosave. It closed my context menu. How nice. Okay, new operation, 2D mill, 2D contour. Okay. And then once again, you see humongous list on the left-hand side, bunch of numbers, bunch of stuff. Let me go ahead and click on the bottom edge. And now it has highlighted in blue the whole bottom edge of the thing. I chose the bottom edge because that way it'll cut down to the bottom edge. If we click the top edge, it won't cut anything. It'll just like trace the top of the material along the top edge. So that's no good. We want to click the bottom edge. So cut through the material to the bottom. Let me see, propagate along Z. What is this? Oh, that's fancy. I didn't know they have these humongous pop-outs. That's cool. And also a bunch of other things. I think for the most part, we tend to keep things as their defaults with a couple of tweaks to like velocities. Let's click on OK. Let's see what happens. 2D contour. Now, like, if I want to simulate this, let's see what happens. If I can generate a tool path for this guy. Oops, it's already valid. Let's simulate then. Okay, so there's my drill bit over there. Oh, okay, so that's no good. It's going to drill into the thing. So I did not set that up correctly. I wanted to go on the outside edge. Let me go back and modify this. Edit. Okay, so where can I see what's going to be inside or outside? Reverse direction. Did that work? Tool orientation. Let's see. Just use the origin. Wrap it around. Press matching. Stock contours. I think this should be good. I've been in a sub option. Let me see. Simulate again. Is it still inside? Okay, now it's outside. Okay, that's good. So I'll click on the play button. Okay. And then I'll trace along the outside edge. I think one thing I did not do correctly on this one was that it's just like straight down into it. Usually you want to like start at the top edge, drill around it, and then go down one layer a little bit lower, drill around it, a little lower, drill around it, a little lower, drill around it until you get the very bottom. So I don't think I set this one up correctly. It should be drilling slowly, layer, millimeter by millimeter down until it gets to the bottom of the material. Let me see. Where the exact setting was. Well, for the bores, those guys are set up correctly. 2D contour, this guy's set up correctly. How did I set up this guy? So just to reiterate, I need to be careful of whether the tool is going to be on the inside or outside edge. That will probably mess things up. It's on the inside edge, so make sure it's on the outside edge. And also consider, I think it automatically does the rotation clockwise, counterclockwise, depending on the direction of motion. Okay. Passes. Okay, here we go. Passes, multiple depths. So I had multiple depths for this good one. That one had multiple depths. So I think the other guy needs multiple depths at 1.5mm increments. Edit. So there's a bunch of subtabs. Let me click on the subtab for multiple depths. And as here goes, multiple depths at 1.5mm increments. Let's click on the OK button. Generating. Let's see. Okay, I like that already. Look at that. Multiple blue lines. Before we had just one blue line along the bottom edge. Now we have multiple blue lines. So I like that. So I made a new 2D contour. I reversed the direction to make sure it's on the outside edge. And now I added multiple depths. Let's go ahead and simulate this. And let's double check it's okay. So once again, always simulate, check your job is good before you send it out. Okay, I like that. Let's go ahead and click on the play button. So first pass is very thin, a mere 1.5mm from the surface. Let's go ahead and speed that guy up. Very nice. Okay, I like that. So I think this is good now. Probably want, before I send this out for real though, I would probably double check, see if the velocities are consistent with the other jobs. Make sure it's gonna be okay. But yeah, it looks good to me. So that was just an overview. I selected the contour, the bottom edge. I checked the direction, make sure it's not on the outer edge. I then added multiple depths to make sure it's not gonna like dig down straight down and like break the drill in one go. I also simulated it, repeatedly simulated it to double check it's gonna be okay. And then finally I can post-process, send it out and print it. Or rather print it, not print it, but mill it out. So a couple steps to it, but always simulate. Simulate is your friend. And it looks nice too. Okay, I think I ran through all the chat questions. Any other questions pop up for you guys? If not, I think this is a good stopping point. We can stop here and come back at 3 o'clock. Let me go grab some water actually. So let me go ahead and stop my share and I will go back and grab some water. I'll be back here soon to answer questions before the 3 o'clock mark. Okay, be right back. Let me pause the recording as well. Pause recording. We'll be back at 3 o'clock. Okay, so we are back at 3 o'clock and let me pull up my screen again and we'll jump right into simulations. Pretty fun stuff. It's rather interesting, as well as later on we'll go over some publication stuff such as renders, camera views, appearances, materials, and some nice stuff like that. Okay, so let me share my screen again. Okay, so you see here on the left, we have good old Froggy here. I was just playing around with appearances. We'll go over to that later. We can have some images for your background. So we'll see more Froggy later, maybe. But in the meantime, let's go over simulations. So simulations, let me pull up my example I pulled up here. Okay. Simulations, there are a lot of simulations you can do in SolidWorks. For the most part though, you probably focus more on like static simulations. And if you're doing like really high speed stuff in fluids, air, water, whatever, then you might want to consider aerodynamics and fluid dynamics, fluid simulations. But we'll first go over statics and then we'll go over to fluids later. So basically this slide highlights how you set up these simulations. I'll actually show you step by step in SolidWorks, but just to give you a high level overview so you don't get lost, here's what's going to happen. I'm first going to make sure here in the top right, make sure I have simulations add in enabled. I have these simulations here. And then you can start making a new study. All right, one thing before I go into any deeper, I have here at the very bottom of the slide, a little X over Simulation Express Design Wizard. I think this one's the free version. If you don't have the educational version of SolidWorks that doesn't have all the plugins, then you might only be limited to this, which means you have certain studies are not available to you. You can only do like the basic static study, force, constant force along one edge or one plane. But if you do have the plugin, then it'll show up here under the add-ins tab. You can just click on the button and it enables a simulation tab here. Once you do that, click on new study. And it has here on the left-hand side, you have a gigantic list of stuff you can do. The default one, static study, that's usually probably what you want to go over. Basically lets you designate a force on a certain face, specify how heavy that force is, what parts of the body are fixed in place, and then you can just press it. So once you click on static, you're then prompted to apply material to the object. So you see here on the very top bar, next to the new study, there's apply material, simulation evaluator, features advisor, external loads, connections, shall run the study. So basically you just run left to right and then your workflow is done. Although you can skip some steps because depending on whether you're working on an assembly or a part. I am working on a part, a singular part, nothing else in here, just this one part. So I can get away with skipping like shell and connections. I only need to focus on apply materials, set the fixtures, and set the loads. So I did here material, set the material. I chose PET plastic because we tend to print in PETG, PETG. So PET was the closest I can find to that. Of course, you can also define your own custom materials. If you are, if you have from the manufacturer, I suppose, the exact information on the materials, then you can specify your own material, but that's kind of advanced. If you don't though, choose one of the defaults. It gets you close enough, at least get you a general idea of how it will behave under stress. And then once you select your material, you then select your fixtures, what's going to be fixed in place, what's not going to move at all. So I selected here the hinges here and here. And then you can also choose different types of fixtures. I chose just fixed geometry, the basic, fixed it in place, not going to move anywhere at all. It's like as if I have anchored it in place in space. It cannot move from those coordinates. Once you have chose your new fixtures, you can then choose your forces. I believe you must select a minimum of one fixture, I think, for it to work. Once you have selected your fixtures, choose forces, select face or faces on which to apply forces or pressures, or even torques if you want. So I selected the inside edge of the claw. I want to see how heavy can it get before it it breaks or something. So I just chose to apply a 10 Newton force applied uniformly on this normal to the surface. You can, of course, do a lot more custom stuff like you want to do it straight left or straight to the right, straight in the X direction without being normal to the surface at certain points. You can do that too. Just takes some more work. But for the most part, clicking on the surface and using the defaults are pretty good as well. The magnitude of the force you apply generally isn't super important for static simulations. It defaults at 1 Newton. You can set it to whatever you want. 1 Newton will do the job though, because when you do run the simulation, it will give you a gradient. And regardless of the strength you use, the gradient will behave the same pretty much, with some exceptions. But the force you apply here does not really matter. Okay, so once again, run left to right from new study, apply material, apply the fixtures, set the forces you're going to apply to it, and then run it. And you might need to click some more buttons if you are doing an assembly. But if you ever get lost, don't know what to do, click on the simulation evaluator or the other advisors, and they'll tell you what to do. Okay, so I don't want to spoil that yet. Okay, let me go ahead and go back here. Hopefully this does not break the aerodynamic simulator I have set up, because it took like 15 minutes to process on my laptop. So aerodynamics, they're annoying. Okay, so let me see if I can pull up the simulation I had earlier. New study? No. Okay, it's pretty fast, not too bad. So I'll just take a new study right now. I'll set a new study, static study. And I'm going to set the material as plastic. Plastics, I want PET. I forgot what it stands for. It's like polyethylene something. Okay, I clicked apply and it seems to be good. Now it's grayed out, that's okay. I want to then select what's going to be fixed in place. And I'm going to select, oh, you see on the left-hand side, simulation advisor. So a nice step-by-step walkthrough, even tells you what it's about to do. So it handholds you through the whole thing. It's really nice. If you get lost, click on the advisors, they help you out. I want this hinge to be fixed, I want this guy to be fixed, and this guy to be fixed. Oops, I did not select them. Add a fixture. Select this guy, select this guy, select this guy. So you notice here, it's those little images. It's like mini coordinate systems pretty much. Ignore all these arrows flying around. That's from the aerodynamics simulator. I don't want to disable it because I think it might break or something, and I have to redo it. Wait another 15 minutes. So I'm not going to do that. Okay, I am done with making the fixtures. Let's go to the next advisor. Oh, interactions. Create more interactions. So interactions is, what is this? I'm done with fixtures. I want to add external load. Add a load. I will then select a face to apply the load to. So add to the inside face. Let's do 10 Newton again, just as the example. So 10 Newton applied uniformly. And then I have material, I have the fixtures, I have the load, I can run it now, and let's see what happens. So let's run the study. It's pretty fast. Okay, so notice here, before this guy was right on the edge of these arrows, now it's being pushed back a bit. So we cannot currently see how good it is right now, but let me see if I can make this a little bit better. So displacement is usually the nicest one you want to do, I think. Displacement is probably the one you want to check out for. Notice the scale on the right, URes. I forgot what that stands for, but it's like displacement in X, Y, and Z. So net displacement, pretty much, from the original point. Red means severe, blue means okay. So 1 by e to the minus 30, it's basically 0, if you remember your exponents. 0 at the bottom, and what is that? 7.2, I presume that's millimeters. 7.2 by 10 to the minus 2, that's tiny. So 10 Newton force is not going to bend this at all. It'll handle that, I think. So let me see if I can edit this. Edit definition. Okay, so notice here, important thing is the display type you're doing. I'm doing resultant displacement, the net displacement in X, Y, and Z. If you want to have it scale only in X, Y, or Z singularly, then choose one of these options. But for the most part, you probably want to do URes. And then deform shape. This one's also really important. Currently, it is at 227 times scale. So what you see here is not what's going to happen. Not what's going to happen in real life. It's exaggerated for so you can see how it goes. True scale is a very minor. A very, very minor change. See that? That's the change. So yeah, by default, they exaggerate it because they want you to see how it's going to change over time. There's also a funny one. Let me see. You can animate it. Yeah, that's pretty nice. Look at that RGB for all you gamers out there. Okay, you can speed it up or do some more frame stuff. I don't really play around with this though. I think you can export it as like an API file. If you want to make another nice GIF or GIF for Discords or something. You can do that. So other types of results you can display. Stress, they're all pretty similar for the most part. I forgot what von Mises was for.
Shows the stress.
Stress. So von Mises stress. Newtons per square meter. Yeah, that sounds about right.
Yeah.
Stress. Force per area. Okay, so a lot of stress at the pinky and the horn over here. That's pretty severe. So I'm gonna be careful about that. So it helps highlight structural deficiencies, and it's rather fast to simulate as well. So something fun to do. And strain, equivalent strain. And a lot of strain here on the pinky. And let me see, that seems okay. And once again, E strain, no units given. Displacement. What is this? This is like a blank one. Okay, resultant displacement. Okay, so that's pretty good. Let me see back at the slide. Yeah, so I just showed you guys changing the definition, making sure the scale is what you want it to. You can define it yourself, 100 times scale, 10 times scale, or just do true scale, 1-to-1. But usually you don't want to do true scale because it's super hard to see the difference. You'll only be able to see the colors. All right, one more thing. Let me see, where was it? Results, displacement, I think it was here. I thought there was a way to chart options, There should be a way to modify the color scale, I believe. I forgot where it was. You might be misremembering. Okay, never mind. That's fine. But yeah, static simulations give you an idea of what's going to change and by how much, approximately. Of course, real world conditions will be different. If you 3D print stuff, the internal structure that you use to print with will not be completely solid unless you do 100% infill. And even then, it still won't be like perfectly uniform. SolidWorks is going to assume it's perfectly uniform inside. So it gives you an idea of where you might expect stuff to break. But if you do it in reality, it probably won't break like that. And of course, in reality, your force is not going to be uniform and uniformly applied to a surface and normal to it at all times. So another trick you can do is if I wanted to have a singular force here, like the size of my pinky poking at it here on 10 newtons, then it's hard to do like this because when you select the surface, it does the whole thing normal to it. What you can do is you can have a small little protrusion, circular cylindrical protrusion here outwards, and then have a force be on that circular face. So you can do that to apply only a force to a certain small area. Have a small recessed or extruded area, so you can apply a small force to that surface. So that's something you can do to get around the restrictions. I see in the chat, you can simulate a fully assembled component, right? Yes. Yeah, I'm scared to do a fully assembled component because it took me 15 minutes to simulate this part in aerodynamics. I don't know how it'll handle statics in a larger assembly, but that sounds pretty fun too. Especially if you get the mates to work correctly, then they'll be like super cool. It'll show you how stress will translate through different mates. Like if two things are screwed together, how stressing one thing will affect the other thing. That might work. That sounds pretty cool though. Something you can do now that you know. So that's your job. Let me see. Okay, so we just talked about static simulations. Once again, new simulation, add the material, add the fixtures, add the forces, and run it, and then you can play around with it, animate it, see the colors, and have fun with that. Okay, any questions on static simulations so far? Had one good one in the chat. Any more? Feel free to speak up or type it out. And as you just saw, you don't need a beefy computer to do static simulations. It's usually pretty fast. But I'm kind of scared to do large assemblies. Okay, I have a question in the chat. Can you do simulation for anything? By anything, I presume parts and assemblies should be okay. I'm not super sure how it will translate through mates because you need to select the fixtures, what's fixed in place, what's not fixed in place. I have not tested with like assemblies and mates, but I presume the principle should be the same. And of course, there's SolidWorks drawings. So you can't apply a force to 2D objects, so can't do that. Okay, very good. Let me show you some of the other studies, actually. That's one thing I want to do. So I just talked about static. There's other ones here. You won't see the aerodynamics or fluid stuff here. That's another plugin. But you see here, static, frequency. If you want to have like another Tacoma Narrows bridge, have it wiggle around and stuff and break, you can do frequency, whatever, or topology design. I haven't really played around with any of these. If you're super worried about like thermal, you can do that too. See how your plastics will deform over time in the heat. That'd be pretty cool. Buckling, fatigue, nonlinear. Ooh, nonlinear. That one took me, I tried to do this one, but it took too long to simulate, so I just closed it. Linear dynamic, submodeling, nonlinear, I presume that just means like varying the force over time. So if you want to do that, you can do that too. But static is the fastest and gets you the easiest idea of what's going to change in your design as you apply forces. So more things here for you to play around with and simulate and animate and check it out. Okay, if there's no more questions, I'll move on to the next section about the dynamic simulations, particularly fluids. Okay, so for fluids, it's pretty similar to what you might expect in the static simulations. First, enable to simulate the plugin. It's called SolidWorks Flow Simulations. It's right to the right of the simulations here. And then you, instead of clicking new, I clicked on wizard because I don't want to go through all the manual steps. I just do wizard. The key points here, there's a bunch of steps here actually, a lot more than what was in the static simulations. But I boiled it down to just 3 that are important. You need to choose whether you're testing the fluids inside or outside the object. So you see here, around an object or inside a pipe, internal or external. And then you also need to choose what sort of fluid you're using air, using water, using gas, something else. And you need to choose the direction that the fluid is traveling. Okay, and then you hit run, it takes a while, and then you play it. So let me just do a mock-up of the, oh no, did it go away? Where'd my motion study here? Okay. Okay, so let me just do a mock-up of what the flow sim is like. So when you hit wizard, you're prompted to do a bunch of stuff. There's a lot of windows here, but just to show you again, important ones are, I skip through unit system. I'm fine with the standards SI units. And also set. You will probably want to select external for the most part. External is what you usually want, especially for like aerodynamics. You want external, an external thing flowing across it. And then I don't exclude anything. I'm fine with that. Well, I should probably exclude internal space actually, but that's fine. I'll keep it. And then if you're worried about water, you use water under liquids, very bottom here, or you can do air up here. And then click on add. You can do multiple fluids at once. Why is it H2O? Okay, cool. And then wall conditions. I don't know what this is. Yeah, so I just left it as is. For things you don't know, leave it as is. The wizard knows what to do. Or you click on help and read into it. But I clicked on next. I skipped through everything I didn't know about. I set the velocity in the x direction to be 1 meter per second. You can also do like set it by, I think, Mach number. So you can do like how your cow is going to be aerodynamic, like Mach 3 or something. So if you want to do aerodynamic cows, you can do that at Mach 3. Click on finish and then it'll start processing. I won't click on finish because it'll take me 15 minutes to process. So trust me, once it's finished, you'll see this. So yeah, you won't see this actually. You will see something else. Let me see if I can show you where it was. Yes. So see here on the left, feature manager, configuration manager, appearances. You probably might remember these guys, but if you click on the arrow, at the very far right, there is the CAM manager. And then to the right of that, simulation flow analysis. So here's where the stuff is. So I previously made project 1 with water, I believe, flowing at 1 meter per second in the X direction. So at the curve. And then let me delete this. Okay. So once your simulation is done, you see nothing. You get this. It looks like nothing's happened. It's a big letdown. So the trick to getting stuff to see stuff is you right click on one of these guys and you hit add something. So I want to see the flow trajectories. I want to see how the water is going to curve away from it. What's going to take the brunt of the force, how it's going to curve away from it. What part of it is water dynamic. So I right click on it, insert. And then it lets me choose pattern. I'll click on this guy. You click on more guys too, I presume. Delete that. I'll just choose one face. Number of points. I'll do 100. Let's see how that goes. Okay. Static or dynamic? That's cool. I think I'll just do static for now. And then crop region, constraints, seems fine to me. Okay, let's go. So once again, if you don't know what it is, the defaults are probably good enough. Okay, I like that. So look at that. It's not a cow, unfortunately, but it is pretty not aerodynamic. Look at all that red stuff right there. So the red stuff says pressure in pascals. So a lot of pressure happening here. It's not curving the air away or the fluid away nicely or softly. It's like crashing head on. So that's not really not that good, but we're not expecting the water to come crushing at it in this direction. So it's okay. So notice how all these arrows curve around. If you remember your calculus classes, if you took calculus, you might remember something about derivatives. Derivatives come into place here, and gradients, and I forgot what it was. Gradients and something else. Derivative fields, or I forgot what it's called. I had it written down here. Vector fields. Yeah, vector fields and gradients are coming into play right here. They're calculating the rate of change at each point, pretty much where the cell's going to go, how much force coming applied at each point. So that's what's happening here. It's really cool. Except they're not doing it in like a grid. They're doing on the path of each one. So you see how stuff curves around it. Nothing's going through the hole. I'm very surprised. It might just because I'm not choosing enough points, but nothing's going through the hole. Okay, that's pretty cool. So you can do this with your own designs. I think you can do it with assemblies, but you will want a beefy computer for that. So be careful. Don't run it on a laptop. I might start burning stuff up. So doing this one small piece took 15 minutes for me. So be careful what you do. Yeah, so there's other stuff too. I did flow trajectories. I presume you can do flow trajectories and select the coordinate planes, the front plane, top plane, rear plane, whatever that was called. And then I'll probably do a lot more things, but I just chose this front place to see what paths will hit it and bounce off of it and ignore everything else kind of thing. So that's what selecting that did. You can select multiple things at once, I believe. And I'll say, show me this, stuff that hits this, and also stuff that hits that. So select what you want, and it'll show you what you want to see. You can do a bunch of other stuff. I didn't play around with the tool that much, but a lot of more tools you can use to see how stuff will change with time, or rather not with time, how stuff will interact with the fluids it's traveling through. Yeah, so once again, you hit the wizard, makes you set the external. I want the external flow. I want the flow with water, and I want the flow with water in what direction and what velocities. What Mach 3 in water or something, whatever you want to do. I unfortunately do not have a cow example to give you, but you can do that yourself. You probably find like a cow SolidWorks part somewhere on the internet and then run it through the simulation. And yeah, brag about it to your friends. Okay, I want to run cables. Okay, any other questions about simulation, static or dynamic before we head on to the next parts? Probably talk about like cable routing and then appearances, renders, photo views, backgrounds, camera views, etc. Yeah, simulation is very cool. It's a nice tool to have. It looks very impressive. So if you want to like beef up some publication material you're sending out to other people, stick a photo on there with your flow simulation. Makes you look very professional. See, look at that. Very cool. Okay, so with that said, any other questions come up, please feel free to use the chat or just interrupt me. I tend to speak quickly and I don't pause enough for questions. So just speak up or type it in chat and we'll see it sooner or later. Okay. Next up is routing cables. I'll do a quick touch on this before I pass it off to Naomi for appearances and stuff. But I'll talk about routing cables real quickly. So yesterday we talked about like swept bosses and stuff where you have like you sketch the cross section of the pipe on one plane, and then on a perpendicular plane you sketch the using a spline the path the pipe's going to take. You could do that to route cables. It's a bit of a hassle though to do it for every single cable because you gotta do a bunch of splines and no one likes splines. But if you don't like splines, and you probably are one of those people who don't like splines, you can probably just use the auto router. There's a nice plugin. There's a plugin for everything on SolidWorks for routing cables and pipes and tubes. So it's right here next to SolidWorks simulation. I can't quite get it to work correctly, but let me just show you where you can find it. I'm going to open up a recent file actually. I want to open up. I'll open up the. I'll open up a small guy. This is kind of big. I'll just open up ROV. Okay, I'll open up the whole robot and I'll see if I can route the cables. I think I tried using this tool, like I tried using it once a day. It couldn't work for me, but I'll see how it'll go usually. Or at least ideally for you guys, you can try to use it. So it could be something you can do to make your designs nice and pretty. You have wires and PCBs and everything on your design. It looks really nice. So currently I have an assembly here. It has a bunch of stuff on it, and Zoom is telling me low system resources to be expected when I open up this file. Okay. So I have here at the very back this is the tether. I use a spline, or not me, but someone else uses a spline and trace along a path to make a path of the pipe. That's going to be having a bunch of stuff inside of it. So if I want to like route these cables now to somewhere else on the robot, going into the electronics enclosure, then I could do that. And to do that, I would check the SolidWorks add-in, make sure it's highlighted. I have the plugin enabled. And then when you have this enabled, it opens up 3 new tabs for you: electrical, piping, and tubing tabs. I will see how piping goes. And I will try to do this. So start a piper on the fly. I will start at a point. So sub-assembly, I want to start it at this guy over here. Okay. Reverse the direction. And then, oops. Okay, choose that guy. And it just as a straight out. I thought there should be a way to, from A to B kind of thing. Routing template. Okay, I think if you select only a starting point, then it should just make a single one. Bends, use flexible hoses, tube, coverings, parameters, C point name. Yeah, I couldn't quite get this to work correctly, but that is not the right direction. But yeah, you couldn't use this. If you get it to, if you figure it out, you can probably use this to simplify your life instead of doing sweeps like this. Sweeps are nice and cool, but you can probably just do the auto router. Okay, so yeah, I'm not going to dig into this too much because I don't tend to use it all that much, but something for you to look out for if you want to use it yourself. Okay, with that said, let me pull up the slides again, and I'll probably pass it off to Naomi now to check a look at appearances, materials, and hopefully we can get through some of the render stuff together. Okay, let me stop my share, and there we go.
All right. So appearances, materials, all this publication stuff isn't really all that useful. Where did SolidWorks go? Oh no. I think my computer is having issues running this many things at once.
Is it not letting you like focus SolidWorks something?
It's where's, oh, there it is.
Dragging the window. I think it works. There we go.
Okay. We're good. So here we have a part, and first we can edit the let me get rid of this so I can show you. It's gone. Okay. So first we can apply scenes and materials and appearances and all of that. So you can apply it up here. We have this edit appearance thing and apply scene. I really like this Urban 5 and this background. I think they're really fun. But yeah. You can get rid of them. But if you want to make a render, you go to SolidWorks add-ins and then you select the Photo View 360, and that will make the Render Tools tab pop up. And then you have those same options up here. So we can also edit the material, but let's try editing the appearance. So we can apply a color. All these fun things. We can also okay, we're not gonna make it like that.
Yeah, I think on the left-hand side of the screen, you should also see like a slightly hidden menu on the right side. Sorry, on the right side of the screen, there's a menu with appearance as well. That lets you just drag and drop stuff. Like you drag and drop a certain style onto the surface and it paints it for you. So if you don't want to go through the whole hassle of manually doing stuff, just drag and drop it. I think it works.
Yeah, my computer doesn't render things very well unless I do a full
Oh,
render.
That's all
So
good.
we're gonna let's go with burnished steel, and I want to make it. Let's make it that kind of color. And then you check the checkbox and it's done, and we can choose a background. I really like the parking lot one. Fun. Okay. So now what's the next thing? Camera views. Okay. So for camera views, it's kind of hidden, but you go to the display manager and then you come over to this little tab here, which is view, scene, lights, and cameras. And then you come down to camera. Oh, it's unsaved. Remember to save your work. And then you click add camera. So now I have a camera in here and I can zoom out, and this window on the right shows what my camera is seeing, and the window on the left allows me to edit the camera. So I can bring it in like this. The yellow dot lets me move the camera, and the red dot lets me move where the camera is aimed. And then I could also pick a target. So if I picked that, then the camera is looking at that line. I can pick this dot right here. And then there are all these controls over here. So I can change things. There's also the angle, which changes the field of view, I think. I changed it to like 70. Yeah, it gives it a bigger FOV. So this is useful if you're testing camera FOVs. We often have to decide what FOV of camera to choose, like 120, 90, that kind of thing. So if we were to position a camera on our CAD and say test between 120 and a 90, we could decide which camera to purchase. So that's good. That'll be good for the render. So now that we have that, we can go to our preview window. So now we're going to start actually trying to make the render. And this honestly might crash my computer with all these things running, but we're going to give it a go. So the preview window is going to show you what your render is going to look like. And while you're editing all your settings, and then the final render button, that's going to actually make your render. Oh, the lights are so dim. Okay, so we need to work with some lighting. Appearance. Where are the lights?
Photo view 360 lights, I believe.
360.
On the left-hand side, let me see if we can annotate on the screen. Yeah, you right-click on that guy or add some more directional lights or ambient lighting. Yeah. Well, it's not too dim. It is pretty dim, actually. Yeah.
It's pretty dim. Okay.
Yeah.
I usually don't mess with the lights, but this is really dim for some reason. So rendering brightness, I can up this, I think. Let's just make it 7 and see what happens. Oh. Okay, I'm going to try changing my background to something normal. And let's see how that changes the preview. All right, the preview looks really horrible, but we're just going to go ahead and render it. So I'm going to click final render. And now it's going to take a little bit, but it's going to go. And now we have a really pretty picture of a box. So obviously this looks much more impressive if you use an impressive part, but I think that'll crash my computer. So you can save this, save image. save. You can save it anywhere you want on your computer, and then you're done. And press the escape button, and you're good. You have your render.
I see a question in the chat. It says, if you have two extrudes on a single part, how can you make the part have two different colors?
You can, okay, how do I get, you can go to the feature tree, which is over here. And if I select this and then go over to the appearances, then I can add the color to that. Yeah, then I can add the color to that specific feature instead of the whole part. Or I can apply a material to that specific feature.
I know you can apply like appearances and stuff to like singular parts. I don't think I've ever tried adding different appearances to different faces or features on the same part. So that's pretty cool. Didn't know that.
Where do you click final? Oh.
Let me share my. You want to share your screen again?
There's a question. So someone asked, where do you click final render? So it's in render tools, right next to preview window, right here, and that'll give you your final render. Okay.
I also wanted to show pretty briefly how we've used camera views on our robot, actually. You heard Naomi mention earlier that we used it for like making sure that the cameras we place in the robot are going to face something important. But let me show you what I meant, or what Naomi meant by that. So I see here, this is a ROV from a couple of years ago. Okay, so I need to I have so many tags, because so many add-ons enabled right now. So let's go ahead and see how these cameras are going to see. Look. It has this weird horn still because I didn't fix that yet. Towards claw. Let's see. Oops. I want to see this guy. Camera view. Okay, I want to see this guy, but in. Yeah, so this guy will give me a simulation of what this camera is going to see. So you can use these as your own tools if you want to add cameras to your robot. So if you can figure out what the FOV is, to do that, we basically aim the camera straight at a whiteboard, measure the length and height and the distance, and then use some trigonometry, figure out the FOV. Because the manufacturer probably gives you like, oh, hey, this is a 90 FOV camera or 120 FOV camera. But then you still need to put it into SolidWorks format, which requires you to, let me see if I can edit, which they require you to give him the theta, the vertical degrees, the distance from whatever you're aiming at, and the height of whatever you're aiming at. So it requires you to know these three parameters in order to get the one you want. So if you want to make your own camera views, be sure to test it out on a whiteboard, do the calculations, write down stuff, and then punch it in here, and you're good to go. Yeah, so that's something you can do and how we've used it ourselves on the robot, actually. So pretty cool. Okay. Let me see. There's also something else I wanted to show, but I forgot what it was. Let me see if I can remember it. I think it was, we talked about pretty much everything we wanted to go over today, actually. We did assemblies, we did mating, we did evaluation tools like the thickness checking, interference checking and stuff. We talked about simulation for a good long while. We talked about static simulations and dynamic simulations. Those are pretty fun. Aerodynamics, that is. We also talked about just now publication stuff, how you make sure that stuff looks nice and looks pretty. Oh yeah, exploded view. That's what I want to go for. So let me see if I can pull up exploded view. I don't think I've set it up correctly for this one. Let me open up a smaller one that won't crash my computer. And I'll see if I can show you exploded view. Okay. It's going to take a while to close it. It's a humongous file. Okay, so I have here good old Froggy as my background for my render. Let me see if I can get exploded view. So exploded view is, as the name suggests, basically blows apart all the parts in a nice split diagram. So I think it's under configurations actually. Let me see if I can add here. What's it? New exploded view. Okay, yeah. So configuration, add a new exploded view. And then let me see. Explode steps. Oh man. When was the last time I used this? I think many years ago. I haven't used this a whole lot because I don't tend to do a lot of publication stuff. But if you want to make exploded views, it's right here, I believe. You do multiple steps. I did not know that actually. Explode step 1. Click on the OK button. Okay. Let's put out a good amount and hit OK. Did that do anything? I don't think it did anything. That's unfortunate. But if you get it to work, it's probably under here, configurations. I need to look into more into this, but it should be there. In the meantime, you can look at Froggy in the background. Okay, so any questions you guys have, feel free to ask about publication stuff, about stuff before, maybe even stuff from yesterday. Feel free, because we're pretty much at the end of our content for today, I believe. But if you have questions, we can keep it going for some longer time. And as you guys think of questions, I'll see if I can figure out exploded view. Okay, I have a question. Let me see. For exploded view, does it get separated based on different folders, or how does it distinguish between different mechanisms? Okay, so let's find out here actually. So there's a bunch of steps, it seems. So let me see. Step 1. I want another step. Okay, step 1 has this and that. Let me add another step to that. Editing explode step 1. I don't want to add to that. I want to add a new step. Okay. I mean, it looks like exploded view distinguishes based on which parts you select. So if you select different parts, they will, of course, explode different things. So I just exploded one part of the claw. You can animate it. It's pretty cool. So if you want to get a nice like blow up part, a blow up view of your robot, you can do that. I want to edit this and I want to add a step. Question in the chat. Can we email you guys if we have any SolidWorks questions after today? I think so. I don't tend to check my email all that often. I should check it more often. But you can always reach out to us. I think, let me see. Should be good. Okay, that one's good. Oh yeah, sure. You can email us. Are you in the workshop planning Discord? You can always reach us there. I don't tend to check Discord often that much. I live under a rock, but you can always reach out to us however you can. I think. Are you in there? I'm not sure. Okay, animate explode. Number 1, number 2. It's pretty cool. Okay, so it looks like you just need to animate the steps. Then you have exploded view right there. Okay, it's pretty neat. Okay. Yeah. I guess I'll put my email in the chat. Although you probably have a better response, right? If you probably join our Slack sometime. Let me see. .edu. Yeah, there we go. So you can email me or email me or both, probably. Probably email both just to make sure one of us reads it. And we can take a look what you're having trouble at. Okay. Do any of you guys have stuff you guys want to show us? If you want our advice on anything, now could be a good time for that. Let me know. We can. I can stop sharing. You can share stuff if you want to take a look at it. As much as it pains me to stop looking at Froggy. Okay, let me edit the scene. Okay, that's a wide one.
Do you guys have a CAD of your robot that we could see?
Another question in the chat. I can try to show our CAD. It might take a few minutes though. Sure, we have some time. Let me stop my share. Yeah, we can give some advice if you have any questions or want any advice or feedback for stuff you're working on. We can take a look and see how we can help. Doesn't have to be in SolidWorks, could be in other stuff too. But SolidWorks is what we're best at. So, but there's still some general tips that apply to pretty much all 3D modeling. So, okay, another question in the chat. Is there a way to animate parts that move? Linear slides. Get the component file straight from manufacturers. Okay, so to get the parts straight from manufacturers, it depends whether they did they give it like a singular monolithic part they cannot adjust at all, or did they give it as like assembly that's multiple parts? If it's an assembly, if they give you an assembly, then it's easier to animate because then you can have a linear mate on the moving part and the fixed part, and that's pretty easy then. But if it is like a singular component, then it's a lot harder to animate. I think you'll see here, we got this piston from the manufacturer, McMaster, and it is one singular part. So this guy in the center cannot move. So in order to move stuff, we just move this guy, and then notice how the centerpiece does not move. The centerpiece should move with the center black piece.
You aren't screen sharing, so.
Oh no. Dang it. Okay, thank you. Yeah, so you see here on the claw, let me go back to a normal view. Show configuration. Okay, so this piston right here, that's straight from the manufacturer. They came as a single part, not an assembly, just a single part. So that means this guy is not movable because it's attached, fixed to this guy. It cannot move it. It's a single object. So to get around it, we just made this movable here. To make the manufacturer part movable, ideally they give you an assembly file with multiple parts that you can animate or mate yourself. If not, though, you may need to remake stuff or see if you can use some more advanced features of SolidWorks to chop an existing monolithic part into multiple subparts, and then you can make it move. So there's ways around it, but it takes more work. And honestly, I don't bother because this gets the job done. So. Let's see. So just to reiterate, for a linear slide like this, you would want a limit distance mate unless you drag it up and down. By animate, did you mean like you want this guy to go by itself forever kind of thing? Maybe you want like take like a screen share, or you want like get like a nice animated video or something of it, like go like this forever. I don't think you can animate it to go like this up and down forever. But you can just do limit distance mate or other mates that will allow certain range of motion. Okay, oh good, glad to answer your question. All right, there's one thing you should not do. Hopefully this does not happen to you, but there might be an add-in called sustainability. Do not click on the sustainability add-in because it will freeze SolidWorks. Yeah, I forgot what it's called. I think it's like sustainability or something. But do not click on sustainability. It's not showing up here, but it froze SolidWorks a lot for me when I tried to click on it. It became a running joke. Just if you wanna stop working, click on sustainability. So yeah, sustainable designs means no more work. But anyways, I want to show you one last thing. SolidWorks, I think it was, or SolidWorks electrical. This is really cool. I want to show you how you can change a PCB into an actual physical part. It's pretty neat. Okay. Oh man, I have too many add-ins loaded. It's not going good. Okay, let me turn off some add-ins. No more routing. I have electrical opened. So I want to go tools. I want to go SolidWorks applications, express products, CAM. Where's my electrical? Electrical. I don't know where the button is. So I will go to the search bar. It's not helping me. Okay, maybe it is SolidWorks. I could have sworn it's electrical. Okay. Okay, let me see. I am at SolidWorks. Open ECAD file. Let me see if I can find a random PCB I have lying around. No thanks. No need for installation. I'll just find a random one I have lying around. Eagle files, CAM design blocks. Where was it? I don't think it'd be in here. Projects. This is really old. 2018. What the? Okay, well, we'll see how this goes. I don't think this will work actually. It might be broken. Yeah, continue anyway. Okay, it broke. Let me look real quick if I can dig up an actual working one. In the meantime, feel free to type in questions in the chat. Be sure to send it to everyone so Naomi can also see it. I will look up for some old PCBs.